Welcome to Get Your FRQ On. This question is from 2014. It is question 6 and it is not calculator active. In the question stem we have a differential equation of the form dy dx equals an expression. We have y equals f of x is the particular solution such that f of 0 equals 1, and we are given that the function f of x is defined everywhere. In part A of the question, we are asked specifically to sketch the solution curve through the point 0, 1, given the slope field provided. So the first thing you're going to want to do here is, since this solution curve is supposed to go through 0, 1, graph that point first. All right, that way you have that point on there, 0, 1. Once we have that point on there, we can follow the slope curve or the slope field to get an idea of what this curve should look like. Some things to pay attention to. Notice it looks like it's increasing here, but somewhere over here we're going to reach a maximum and then it's going to start decreasing. It's going to be decreasing, well, actually increasing, but if you look at it in reverse, it's going down towards a minimum here and then it'll go back up this way. So just make sure that you follow the slope field. Don't go beyond the border of the slope field, and don't draw anything that clearly doesn't match with what the slope field is trying to communicate to you. All right, so following the different marks in the slope field, we would get something that looks like this. In part B of this question, we are asked to write the equation for the tangent line at 0, 1 and use it to approximate f of 0.2. In order to get the slope of this tangent line, we can just evaluate the expression for dy dx at the point 0, 1. So if we do that, we're going to get 3 minus 1 times the cosine of 0, which is 2 times 1, which is 2. So the slope of our tangent line is 2. And then we can use the point 0, 1 to write this in point slope form. And then for this problem, it's going to be convenient to have this in slope intercept form, but not necessary. So we have this tangent line y equals 2x plus 1, and if we want to approximate f of 0.2, we can just replace y with f of 0.2 and replace x with 0.2, and f of 0.2 would be 2 times 0.2 plus 1, or just 1.4. In part C, we are asked to find the particular solution y equals f of x such that f of 0 is 1. Now, in order to find the particular solution, we will have to solve the differential equation. And for the AB exam, really the only way you have to solve these would be separation of variables, given the way that dy dx is presented. That is the expectation. Many of the scoring guidelines for questions like this state that if you don't use separation of variables, you could fail to earn any of the points for this particular part. So make sure you understand that when you see a differential equation and you're asked to find a particular solution, if it can be solved with separation of variables, that is the expectation. All right, so I have my dy dx, that's 3 minus y times cosine x. If I divide both sides by 3 minus y and multiply both sides by dx, I get dy over 3 minus y equals cosine x dx. Anti-differentiate both sides. And then, all right, so the antiderivative of dy over 3 minus y would be negative natural log of the absolute value of 3 minus y. And the antiderivative of cosine x is going to be sine x plus a constant. All right, we also have to make sure that our solution satisfies the initial condition that f of 0 equals 1. So we're going to need to solve for a specific value of c here, and we're going to do that by plugging 0 in for x and 1 in for y. So we have the negative natural log of 3 minus 1 equals sine of 0 plus c. Sine of 0 is 0, 3 minus 1 is 2, so negative natural log of 2 is equal to our constant. And what this does is this now allows us to write a more specific or more particular solution for f of x. All right, we know now that c is negative natural log 2, so I get negative natural log of absolute value of 3 minus y equals sine of x minus natural log of 2. I switch the negative sign to the other side just so I can get rid of it in front of the natural log. It does switch the terms on the right-hand side. And so we get natural log of absolute value of 3 minus y equals natural log of 2 minus sine of x, which, if we exponentiate both sides, we're going to get 3 minus y equals e to the natural log 2 minus sine of x. Now at this point, we still do need to solve for y, so at the very least you'd have to add y to both sides and subtract e to the natural log of 2 minus sine x. But you might also want to clean up the natural log of 2 minus sine x. E to the natural log 2 is 2. So you could write this as y equals 3 minus 2 times e to the minus sine x, although that last expression might not be necessary. You could leave it as natural log 2 minus sine x in the exponent, but you would still have to solve for y.